Okay, I think everyone's joined. There might be one person missing, but it's fine. We can get going. All right, guys, welcome to the final exam prep training. Um, we've made it a long way and we're almost there. There's not too much left to do, pretty much just regression. And I hope that the way I've structured the regression training today, because it is quite different from the way the lecturer did it for IPCOM. But listen, I've taught regression a lot, and I find that the way that they teach regression makes it way more complicated than it needs to be. So hopefully we'll be fine with that. And then we're going to do a bit of a mock exam kind of situation. So instead of doing practice question, solution, you guys are actually just going to do all the questions, and then at the end, we're going to go through the solutions and troubleshoot any problems. Okay. And like I said yesterday, I really am challenging you to not look at your notes when you do this mock exam because it's going to give you the best indicator of where you're at for the exam and also which kinds of questions you automatically feel comfortable with and which ones you don't. So you know where to focus. Can everyone see my screen and hear me well and all of that good stuff? Just give me a thumbs up. Awesome. Okay, so your introduction to regression. It is the most commonly used analysis to test a cause and effect dynamic between variables. Okay, so most of the time when you're doing original research, what you want to aim for is to be able to do a regression analysis because then it allows you to say that like X causes a change in Y. So all your variables for regression have to be interval ratio. And it is based on the same linear relationship as a Pearson's R. Okay, so if you plotted raw data on a graph, it would be a scatter plot, right? And the regression line that runs through the scatter plot is literally your regression. Okay, so you can think of regression almost as like the test of significance version of Pearson's R. So you're going to also notice some similarities between this and Pearson's R. Okay, you can have a simple regression, which is a bivariate situation where you only have one IV and you always only have one DV. Or you can have a multiple regression, which is the multivariate option, where you have more than one IV. Okay, but you always only have one DV. Now, regression at its most basic form. Okay, this is really important. It's for all the tests, actually, it's important to, distill it to its most basic form. What is it testing? Regression is, does X have an effect on Y? Okay, so the word effect is specific to regression. Another thing we do with regression, which is along similar lines, can we predict Y using X? Okay, so the word predict, prediction, predictor variable, all associated with regression. Your X variable is actually often called your predictor variable. Okay. So basically, if X has an effect on Y, that means we can go backwards. We can predict Y using X. And then, of course, can we generalize about the population, which is true for all of the tests of significance. Okay, for the sake of your open regression questions, guys, I guarantee you there's going to be a regression question, an open regression, because they haven't tested you on it yet. So they need to test you on it. It's going to be there. There are two types of open regression questions. The first one is a hand calculation using the regression formula, where we're able to predict the Y value using a specific X value that they provide in the question. Okay. The second part of the question, or second type of question, is the actual test of significance, which involves hypotheses and p-values and rejecting H0 and all the usual stuff. Okay. And from that second one, we can conclude, does X have an effect on Y and what effect? Okay. So if we look at a regression line, depending on what level of math you did in high school, you would have done this. It's called a linear function or a linear graph, and it has its own formula. So in this course, we say y hat equals b0 plus b1x, but you can also know it as y equals mx plus c, ax plus q. It doesn't really matter what the symbols are. This is your basic linear formula. So your b0 is your y-intercept. Okay, so intercept means that it is the point where the line cuts the y-axis. So it's here at 10. Okay, so it cuts the y-axis. At that point where the y-axis is cut, x is at 0. Okay, so this is just true about the b0 and the intercept at all times. When x is equal to 0, so when x is there, then the predicted y value is the value of the b0. Okay. So that's first thing. Your b0 is something you're going to find in the SPSS output. So basically for regression, you need output to do anything. Like you just need the output. So you're going to find your b0 in the output, and you need to look for what's called the constant. That is your b0. Okay. And then your b1 in the formula is your slope. Okay, so the slope literally refers to how steep your regression line is. And if you have to explain what the slope means in plain English, it means if x increases by 1 unit, okay, so whatever the unit may be, depends on what the variable is, but you increase by 1 unit, y will increase by the value of the b1. Okay, that's the plain English description of the slope. Now in SPSS, our b1 or our slope is called the unstandardized regression coefficient, which is the symbol capital B. Okay, so that's where we're going to be looking for our b1. All of this clear so far? Yeah, okay. So when I said that the first kind of question is the hand calculation, this is the formula that you're going to use. For some reason, and unfortunately, this formula, it does not appear on your formula sheet. So this one you do actually have to study off by heart. Okay, if we look at this example, so you can see for the x-axis, our x variable is hospital beds per 1,000 people, and our y variable is life expectancy at birth. So the kind of question we would ask with the regression is, does the number of hospital beds per 1,000 people have an effect on life expectancy at birth? And we can also ask, can we predict the life expectancy at birth by the number of hospital beds? Okay, so to find your B0 and your B1, so when you get your SPSS output for regression, you're going to get 3 tables. Okay, your coefficients table is your third one. And I want you to only pay attention to the unstandardized coefficients with the capital B column. Okay, you can see your constant is written there. So 45.021 is your B0. And your B1 is always right underneath that, and in alignment with your independent variable, hospital beds per 1,000 people. Okay, and that is a complete formula. Now all you need to answer a question is a specific x value to be able to predict the y value. Now, if we talk about what these two things mean in terms of the meaning of the B0 and the B1. Okay, so the B0 is 45.021. That means that the regression line cuts the y-axis at this point, at 45.021. Okay, so when x is equal to 0, the value of y is 45.021. Now for your B1, what this means in terms of these variables is, so x variable is hospital beds. When we increase hospital beds by 1 bed, okay, so the unit is a bed. Hospital beds increases by 1 bed. That means that life expectancy increases by 8.122 years. Okay, why does it increase? Because it's a positive here. Your B1 can definitely be negative. because all that indicates is a negative like effect. So what you would say is that hypothetically, if we increase hospital beds by 1 bed, life expectancy would decrease by this many years. Okay. Everyone clear on this so far? Cool. Okay, so the kind of question you would get for this hand calculation, really simple. Once you've filled in your B0 and your B1 inside your formula, they will ask you, what is the predicted life expectancy when there are 2 hospital beds per 1,000 people? Okay, so they've given you a specific X value, the number 2. So you put it into your formula and you get an expected Y value of 61.27 years. So your conclusion would be when there are 2 hospital beds per 1,000 people, the predicted life expectancy is 61.27 years. Okay. Easy peasy, clear. Okay, so what we just did, this example, we had one independent variable, right? So that was a simple regression example. Oh yes, Laura.
I just have a question about the last slide,
Yeah.
about the conclusion.
Mm-hmm.
So are we gonna say if it's just like a simple calculation, not the test of significance, are we gonna say, or do we have to say in the population, or is this not about a population?
It is about a population. Um,
Because they taught us
but
to
you're not
like
using
always.
this, yeah, you're not using this to generalize about the population just yet.
Okay,
Um,
so no
you know
population.
what? You are actually, this still is about populations. I'm gonna advise that you do say in the population.
Okay, thank you.
Yeah, yeah. Okay. Okay, so if you do the multiple regression, so you have more than one independent variable. So your formula begins the same way, y hat equals b0 plus b1x, yeah? And then you just add on plus b2x2, however many independents you have. So in this case, if you look at the output, we have 3 independent variables sitting in the coefficients table. So we would say plus b2x2 plus b3x3. And that would be our complete formula. Okay. Our B0 is our constant, so 6.683 here. And our B1 for independent variable 1 is for age negative 0.016. Okay, so because it's negative, you make sure you put that in brackets. Okay, so just to keep the structure of the formula. But basically that indicates that when age increases by 1 year, that means that happiness decreases by 0.016. Okay. So our dependent variable is happiness. And then your B2 will be right below that, aligned with the next independent, which in this case is trust. And you put it there. And then the next one, 0.041, is your B3. Okay, so they've actually written out the words age, trust, religiosity, but you can also write X1, X2, and X3. And then you have a complete multiple regression formula, and you're ready for them to give you specific X values. So how happy do we expect someone to be? So they're asking you to predict Y, who is 22 years old, so 22 for age, and who scores a 4 on trust and a 3 on religiosity. Okay, so 3 specific X values to put into your formula. You put it all in your calculator, and you'll get a predicted happiness score of 7.334 or 7.33. Okay. And that is all there is to this first kind of question. Does anyone have any concerns about this?
I have one question. Will they ask about the test statistics or the p-value here, or?
Okay, so you're getting ahead of yourself. Remember I said that there's 2 types of questions in regression? We're dealing with the first kind of question. The second type of question is the one with hypotheses and p-values and all that. So it's the same output for these two types of questions. Okay, they're not going to give you a different output. It's just what the kind of question that they're asking you. Okay, so we're getting there.
Okay, thank you.
Yeah. So now we're getting into the regression test of significance. Okay, so the usual hypotheses and rejecting H0 and all that. Okay, so the two tests that are inside a regression, and you must interpret both, and you must have hypotheses for both. Okay, it's really annoying. The first one is an F test. So you might remember the F test is actually an ANOVA. Okay, but it's not the ANOVA that you know from an ANOVA question. This tests the regression model, like is the model significant? So with regression, you can have a simple regression when you only have one IV, but then if you have a multiple regression, then you have like 3 IVs. The model includes all 3 IVs. That's what the F test will test, okay? Whereas the T test tests the specific effects of each separate IV, okay? So the model encompasses all 3, and then for the T test, you'll do 3 different interpretations. So your H0 and your H1 for your F test. So in the population, R square is 0. Y cannot be predicted by X. Okay, this shouldn't surprise you that your H0 is your baseline, right? You have to say that Y cannot be predicted by X because that's the thing you have to prove. So that'll be in your H1. And we keep our H1 non-directional. So in the population, R square is not 0. To some extent, Y can be predicted by X. Okay, guys, obviously, just for X and Y, you need to write the actual variables in the question. You don't put X and Y, and don't put IVDV, please, ever. You always need to be as specific to the question as possible. Okay, so for your F test, you're going to have a p-value. You're going to reject your H0, hopefully, and maybe accept your H1 as per usual. Okay, and then the second part, and it's all one output, by the way. There's both these tests included in one output. Okay, then for your T test, your H0 is that in the population, X has no effect on Y. Yeah, and then your H1 is in the population, X has an effect on Y. And when you conclude, not only will you reject your H0 and accept your H1, but you're going to be specific about the effect that X has on Y. Okay, what's this R square in the F test? Okay, the R square is mentioned in the H0 and H1 of the F test. So what is it talking about? The R square shows us how well we are able to predict Y using our X variables. So it is a measure of goodness of fit or a measure of accuracy. Okay, so the higher the R square, the more accurately we're able to predict Y. They will definitely ask you, like, I don't have a doubt in my mind, they will ask you, please interpret or explain the R square value. Okay, and there's a specific sentence that they want from you as the response. And here it is. The R square value is the proportion of the variance in the dependent variable that can be explained by your independent variable. Okay, so the dependent variable means there's all sorts of variation going on in your dependent variable. How much of it is being explained by your IV? Okay, that is your R square. So with your variables, it would say something like the R square is the proportion of the variance in life expectancy that can be explained by the number of hospital beds per 1,000 people. Your R square in your output is going to be a number from 0.0 to 1.0. In the model summary table, which is your very first table that you get in your output, when you answer a specific question about the produced R square value, you convert to a percentage. So R square is always going to be like a decimal because it's between 0 and 1, right? So if your R square is 0.445, that means that 44.5% of the variance in life expectancy can be explained by the number of hospital beds per 1,000 people. Okay, so if you're going to study anything about the R square, let it be that sentence. And this is what it would look like in your model summary table. Okay, your R square 0.445. Okay, now let's go through actually interpreting our F-test. So you're going to get 3 tables for regression. You got model summary, ANOVA, coefficients. Okay. In your model summary and your ANOVA is where you conclude on your F-test. So your R square value in this case is 0.097. And if you look at your ANOVA, your p-value is lower than alpha, and you've got your F value, your test statistic, if they ask for it. Okay, because it's low, you would reject the H0 of the F-test. Okay, and you accept the H1, that R square is not 0. R square is 0.097. And to some extent, Y can be predicted by X. So in this case, happiness can be predicted by age, trust, and religiosity. Okay. Now that you've established that the model as a whole is significant, you can move to the specific effects of each IV in the t-test. And that's in your 3rd table, which we've already seen. Yeah, we've already looked at the coefficients table, right? But we were looking at it when doing the regression formula hand calculation, and we paid attention to the first column with capital B. Now, in this kind of question, we completely ignore that column and we only focus on our p-value and our beta value, which is called the standardized coefficient. Okay, so your p-value operates as always. If it's low, it tells you to reject H0 and that there is a significant effect present. But your beta tells you specifically what kind of effect is going on here. And the beta operates exactly the same way as the Pearson's R. Okay, so it's a standardized value, so it's always between -1 and +1. Okay, you interpret it by using strength and direction. Okay, the strength guidelines are exactly the same as Pearson's R, and direction is positive or negative. And so it describes the effect. So we have a look here. The very first p-value is not our concern because that aligns with the constant. Okay, that means nothing to us. We only want to interpret p-values that align with the IVs. So 0.000, in fact, all of the p-values you can see are significant. Okay, that would mean you reject the H0, that there's no effect, and you accept the H1, that there is a significant effect. And then you write a sentence for each independent variable on its own. So if we look at the beta, this one is for the effect of age on happiness. Okay, your beta is negative, so it's a negative effect. And in terms of the strength guidelines, it fits into the weak or the small category. Okay, so the way you would phrase this is age has a negative, weak, and significant effect on happiness. Okay, and then you're done. And then you move on to the next IV. And the beta is positive, also still fits into the weak category. So trust has a positive, weak, and significant effect on happiness. Okay, and then and religiosity, the last one, positive, and I would say very weak. Okay, so religiosity has a positive, very weak, and significant effect on happiness. Okay, and that's all there is to interpreting regression. So if you think about it, when you're moving through your output, your eye is kind of moving in a diagonal line. So you start with your eye at R square, and then you move towards the right as you go down towards the ANOVA p-value, and then you keep moving in the same diagonal line to see your p-value and your beta in your coefficients table. Okay, and however many IVs there are is the number of sentences you need at this stage.
So for the F-test, do you only interpret the p-value?
Yeah, you only interpret the p-value of the ANOVA. If they ask you to report the test statistic, then you give them F, but F doesn't decide anything for you. It's always the p-value.
Okay.
Yeah. Does anyone else have any questions about
What if here the p is significant?
what if the p is significant?
Yeah. Do I also say something about it, or just leave it like that?
So it is included in the conclusion here. So age has a negative, small, or weak, insignificant effect on
Oh,
happiness.
sorry, I meant not significant.
Okay, if it's not significant, then you don't need to mention it. You only report your significant results. Unless they ask you to say, please report all results, or please report both your significant and insignificant results. Then you just say that, say, for example, say the age p-value was high. Then you would just say that age has no significant effect on happiness. Does that make sense?
Yes, okay, thank you.
And Laura?
I was just wondering, in which case, or do we not at all have to report the test statistics? Because, or only when they ask for it? Because we learned like the 4 steps where we always have to report test statistic in like test of significance. So
You're talking about the 4 steps of calculating a test of significance by hand, where you have to calculate the test statistic, which is your obtained value, and compare it with a critical.
no, I mean in the SPSS test, like the 4 steps of interpreting the output. It was like sample description, then the test statistic and p-value, decision, and then conclusion.
Okay. So yeah, they tell you to pay attention to your test statistics. But what they require from you in terms of reporting in this course is actually, they don't require you to report the test statistic automatically. They require your p-values. And they often do ask for test statistic. They often say like report all the relevant statistics, including the test statistics. So it's maybe safer to include the test statistic in your conclusion. Like
Okay.
I tell you not to, because
Yeah.
who knows, maybe that's what they want. So yeah,
Okay.
report it, and then, but it doesn't make any decisions for you. Yeah.
Okay, can you, like, maybe because I'm a bit confused about the order where we have to report what for this test, can you maybe give us a run
Sure.
of it?
Julia, do you want to wait to ask a question, or can I do this first and then you ask?
Oh, I can wait.
All right. So you start with your hypotheses always, right? Which is not there. There we go. So you start by writing down both sets of hypotheses for your F-test and your T-test. Okay, then you start with your F-test. Okay, you have a look at your R-square and you have a look at your p-value and you interpret. So p is low. So you say, therefore, reject H0 and accept the H1 that the R-square is not 0. Y can be predicted by X, and then you provide the R-square value, and then, like we talked about, provide the F value, provide your P value. Okay. Then you move on to your T-test, okay? And this is where this conclusion matters. So you would say, okay, P-value is low for the IVH, so I would reject the H0. Age has a negative, small, insignificant effect on happiness. Then you move to the next IV. Okay, P is low, also reject that H0. And then trust has a positive, small, insignificant effect on happiness. Then for the final variable, do it all again, and then you're done. Okay, so basically, it's almost like for the T-test, because it goes the specific effect of each IV, your H0 kind of applies to each one when you go down the list. Does that answer your question, Laura?
Yes, kind of it did. Sorry, but also for beta, do we have to write it down at all, or do we just have to say in the conclusion
Yeah.
weak, negative, whatever?
Yeah, you do need to actually give your beta.
Okay.
Yeah.
And then for the R squared, from the first, like from the F test.
Yeah. You give the
And-
R square when you conclude about the F test. So when you reject your H0,
Okay.
accept your H1, provide your R square.
So we have to after we interpreted the F test, we have to give like a conclusion already and then move on to the T test and say in the conclusion like the percentage of R squared or
Yeah.
not? Okay.
Not the percentage actually. So when you're just reporting, when you just say like, this is my R square, you give it as it is. So R square equals 0.097. You only convert it to a percentage when they ask you a question like, interpret the R square value. Then you have to convert to a percentage so that it fits into the sentence.
Okay, thank you so much.
Okay, Julia, you're up.
Actually, how would you interpret the R square? I think you said it, but I forgot, sorry.
Sure.
How to interpret the R square if you have to give it like a percentage and then.
Sure. Yeah, I'll go back to that. Sorry, Julia, what did you want to ask?
So the R square, is it just that I write it down? So I write down the F value for the F test and the P value, and I write down the R square value, but how far do I include the value of R square into my conclusion? Do I always have to use the one sentence you told us, or do I not?
Okay, so sorry. When you're reporting statistics to support your conclusions about the H0, you just report the statistics as they are. So you say R square equals 0.097, F equals 1172.56, and P is less than 0.001. You just write them as they are, okay? The sentence applies to when they ask you a specific question about R square. Like if you go back to your week 7 assignment, you'll see it right there. They'll say interpret the R square value. And that's when you need the specific sentence I gave you and you convert to a percentage, which I'm going to show you again now. Okay, it's the one highlighted in yellow at the bottom. Okay, so if your R square is 0.445, right? If you're including it as your part of your conclusion of your F test, then you just write R square equals 0.445, done. And then if they ask you, please interpret the value of the R square, then you need to write 44.5% of the variance in the DV can be explained by the IVs. Okay, does that answer everybody's question?
Yes, and I also have another question. So is it always like when it's about the test of significance and regression analysis, if it's always so my first step is the F test, my second step is the T test, or is it different tasks?
No, it's all together. So they can always ask you separately. They can break it down, like open question 3.1 is please do the F test, 3.2 is please do the T test. They can always do that as well. But a full regression interpretation involves both. So this is something that will become so much clearer in second year when you start doing quantitative methods specifically for research purposes. When you interpret regression, you've got to interpret the full output. In fact, you don't even need to use the regression formula usually. It's just something they want you to know for this course. But they can put both types of regression questions in one open question. Okay, you've just got to pay attention to what they're actually asking you. Okay, are they asking you to formulate hypotheses and conclude on them? Or are they giving you specific X values to use to predict Y? Those are the kinds of things you got to pick up on in the question, which we will do an example in the mock exam. So for the regression, the first question we're going to do is a regression question, and we'll go through it together. Okay. All right, any other questions before we move on into theory? Theory is dense. No? Okay. Okay, my favorite thing in the world to teach is regression theory. Your lecture slides for regression are awful. Awful, awful, awful. They mix and match between the regression formula, the test of significance, the theory, like it's all over the place. So if we go back to our basic regression line on a scatter plot. Now remember what our regression line is doing is that it's predicting y. So we're trying to know what y is going to be, even if we don't have the data, right? But if we put our regression line through a scatter plot, you can see that the actual blue dots, that represents what occurred in the sample, okay? And they're not sitting perfectly on our regression line, okay? So if you look here, for someone who earns 2,500 euros, the regression line predicted their happiness at 6. Okay, but what actually happened in the data, okay, you can see with this blue dot up here, the person in the sample who earns 2,500 euros, their happiness level is actually at 8. Okay, so this difference between what the regression line predicted for y and what actually happened in the sample for y, that difference there is called the prediction error. Okay, and in this example, the prediction error is 2, because we predicted 6 and the reality is 8. There's a difference of 2 points there. Everyone clear on that? Is that simple? Okay. Now, if we talk about prediction errors, okay, it's obviously talking about to what extent is our regression line being inaccurate in predicting y. So if we basically looked at the prediction error for every single x value or every single y value in the sample, okay, so the distance between what we predicted for y and what actually happened. We take each one, so it's illustrated by the red dotted lines here. If we took each prediction error and we squared it and we summed them all up, okay, we would get what's called the SSR, or it's the sum of squared residuals. Okay. So the SSR is our measure of inaccuracy for the regression line. It tells us, yeah, how wrong we are with prediction. So basically what we want ideally is a small SSR. We want the smallest SSR possible because that indicates that the prediction errors are small as well. Now, remember with R square is a measure of accuracy, okay? A high R square indicates that we're able to predict Y very well. So basically, a small SSR means a high R square. So low inaccuracy means high accuracy. Yeah? Does that make sense to everybody? Yeah? Okay, this is key. This is like the beginning of understanding the rest of the theory. So if it's not clear, please let me know.
I just have one question. So the SSR is exactly like it's the measure of inaccuracy, but you said something about it's the sum of the differences?
It's the sum of squared residuals. So if you look on the right-hand side with all this ugly text in there, it's it says the sum of squared residuals. So residual is, it literally comes from the word residue, right? So it's like leftover. It's another word used for prediction error. But yeah, essentially that's what this is you're squaring and you're summing all of the prediction errors.
Okay, thank you.
Okay, you tell me which of these two scatter plots has the smaller SSR?
The right one.
Yeah, the right one. Okay, because you can see the dots are closer to the line, which means the line is predicting the data more accurately. Your prediction errors will be smaller, which means your SSR will be smaller. Okay, what if we did the same thing, but instead of looking at the regression line, we looked at the mean? Because we use the mean to try and get a sense of what's going on in data a lot, right? So if we look at the mean life expectancy is 51.52. Okay. So it's sitting right there in the middle of the data, which is where the mean likes to sit. And we look at the scatter plot. And you can see that the prediction errors between the dots, data points, and the mean are quite long. Okay, so if we want a measure of inaccuracy of using the mean line to predict y, then we would do the same thing with the prediction errors, right? We'd take each one, we'd square it, we'd sum it up, and that would give us our overall measure of inaccuracy. This is called the SST. I didn't actually write it here, but the SST stands for the total sum of squares. Okay. So they usually refer to it as the SST, but it's also called the SSY. I do not know why they have two different names for it. Okay, so you just need to know that they're the same thing, but it's more standard practice to say SST. So do you see, now we've got an overall measure of inaccuracy for regression, and we've got an overall measure of inaccuracy for the mean. Okay, so what do you think we're trying to do here? Like, what are we trying to prove? Figuring out which who's more accurate is basically the question we're trying to ask. Are we more accurate in predicting y when we use regression or when we use the mean? Okay. So this is the same data, the same scatter plot on both sides. If you look at the mean on the left-hand side and the regression on the right-hand side, you can see that the prediction errors for regression are shorter. Okay, which means that the regression is more accurate to use for prediction purposes. And of course, that is expressed mathematically too. Okay, so if you want to know how much regression has improved upon the mean, okay, well, you would take your total sum of squares. So what would the inaccuracy be using the mean? And you subtract the inaccuracy of the regression, and what you have left is the SSM, which is called your model sum of squares. Okay, so your model sum of squares represents the amount by which regression has improved upon the mean as a prediction tool. Okay. Does that make sense to everybody? Yeah? Okay. Okay, so how does all of this fit into what we actually do when we run this test of significance? It all has to do with the R-square. Okay, so far we've been looking at the measure of inaccuracy, and so R-square is conversely the how accurate we're being. So if our model sum of squares, okay, so this is how much we've improved upon our prediction abilities. If the model sum of squares is the amount of variance in y that can be explained by the model, okay, and your SST is the total amount of variance in y. Okay, so if you go back to the mean one, I actually wanted to point this out to you. All right, this one, if we look at the mean, okay? Here, I actually wrote it down, okay. Do you see that this would also be an expression of variance, deviation from the mean, right? So in week 2, when we look at variance and we look at standard deviation, okay? What do we look at? What is variance? Well, we're looking at how much does the data vary around the mean. Okay, and that's exactly what we're looking here. We've got the mean, and then we've got the deviations from the mean. We're just calling them prediction errors because now we're doing regression, but it's the same thing. It's a deviation. So this measure of inaccuracy is also a way of expressing variance. Okay, I'm done with that. Okay, so coming back to this, that's why your SST refers to the total amount of variance in Y. And your model sum of squares is the amount of variance in Y that can be explained by the model. Okay, so basically it's that difference in improvement. So what this means is that your R square is your SSM divided by your SST, and that's what creates the decimal, the fraction. Okay. So it's basically how much variance is explained by the model over how much total variance in Y there is. And how do we express the R square? It's the proportion of the variance in Y that can be explained by our independence. Okay, Y has a lot of variance. How much of it? What proportion of it is explained by this regression model? Okay, so what you have to remember from all this is I want you to remember this, what is the model sum of squares? What does it represent? The improvement in predictive ability, okay? Your SST is the measure of inaccuracy of using the mean to predict. Or SSR, the measure of inaccuracy using the regression to predict. Okay. I've already told you what I want you to remember about the R square. This sentence is key. And that the R square is equal to SSM divided by SST. Even if you don't understand why that is the case, why that's the equation, it doesn't matter. They're going to ask you much more in terms of understanding of SSR, SST, SSM on their own versus understanding how you get the R square value. Okay, does anyone have any questions about this? That's awesome. Okay, you've got some assumptions of regression, basically things that need to be true for regression to work, okay? And they're very similar to the assumptions of Pearson's R. So your first one is linearity. So this is a linear relationship, meaning the dynamic between the variables is basically one increases and the other either increases or decreases. It's really simple. The second one is homoscedasticity. That's also an assumption of Pearson's R. And that just means we need, my voice is going a bit, sorry. We need a consistency in how our dots are spread out in the scatter plot. So if you look on the left-hand side, this picture, the dots are pretty evenly spaced, like over the line, they're pretty consistent. Whereas on the right-hand side, they start out really close together and then they start spreading out. So that is inconsistent. That's an example of heteroscedasticity, which we don't want. And the last one is lack of multicollinearity. So this means that you cannot have a very strong correlation between your independent variables in regression. Okay, so your R, and this is a test you actually have to run when you're doing real research to make sure that your R value is not greater than 0.8. Okay, and what happens if there is a very strong correlation between your independents? It causes incorrect high p-values, okay, which means that you are making type 2 errors, most likely, because you're going to be retaining H0s when you should be rejecting, possibly. It underestimates the R square. So, it tells you that you're not predicting Y very well, where you may be. Unreliable coefficients, and the only solution when you do have IVs that correlate is to remove the variables that are causing the correlation. Okay. And that's just theory, pretty easy to understand. And yeah, I think that might be, oh no, one more thing. Finally, interaction effects. Okay. So this happens only in a multiple regression when you have multiple independent variables. And basically the presence of another independent variable. Yes, I see your hand. Laura, what's up?
Can you just go back one slide because I didn't have enough time to it.
Sure. You do have access to these slides, eh, guys? You should have.
Okay. Yeah, thank you. That's fine then.
You make your own notes,
Yeah.
obviously. Okay, so what happens with an interaction is that the presence of another independent variable either strengthens the effect, or what happens is that you can have an independent variable that does not have an effect on the DV, but when you include another independent variable, then suddenly it becomes effective. Okay, so basically it's when the presence of the independent variables, the multiple independent variables, enhances the effect. Okay. So simple example is, let's say we investigate if weight training has an effect on muscle mass. And this is a simple regression, and we call that a main effect when we look at one independent variable's effect on its own. Okay, so then we add another independent variable to our regression model, which could amplify or enhance the effect, protein intake. Okay, so now when we do a multiple regression, we'd include both. Does weight training and protein intake have an effect on muscle mass? Okay. This would be a multiple regression with an interaction effect. Do you think that we just improved upon our model's ability to predict muscle mass? What do you think?
Logically, I would say yes.
Yes. Okay, so weight training might already have its own significant main effect. Okay, but from what the fitness industry and fitness science knows is that weight training doesn't actually do that much unless you're eating enough protein to actually support muscle growth. Okay, so even though weight training may be significant on its own, the effect becomes stronger with the presence of protein intake. And that's it, guys. That's all there is to regression. Is there anything you want me to go over again before we start our practice time? We are going to take a break, obviously. But yeah, let me know. No? Okay. So we're going to take a 15-minute-ish break, and then we're going to dive right into the practice stuff. Okay. So if you guys can all be back at, what is it going to be? 11:10. Yeah. I'll see you in a bit. All right, guys, everyone back. Cool. Okay, let's head into the practice time. So, we are starting with some multiple choice questions. And I would like you to, whatever you're working on, a piece of paper or digitally, whatever, I want you to write down your own answers for these, and then we're going to go through them after we've gone through all of the multiple choice questions. Okay. So there are 10 questions, I think. I'm going to give you, let me think. I'm going to give you until 20 past. Yeah, until 20 past 11 to do the questions. And you know what? I'm going to change slides every minute. Okay. Okay, changing slides now. Okay, changing slides. changing slides. Okay, changing. Okay, last slide. Okay, that's it for multiple choice. We're ready to go through the solutions. How did you guys find it?
I have a question, just for myself to review it later.
Mhm.
If you're not going to fully explain it now. So the type 1, 2, and 3 errors,
Mhm.
I think I missed it maybe in the slides or
Okay.
something, but when did we discuss it so I can review it after this?
We looked at the type 1 and it's only type 1 and type 2. So I put type 3 as something to throw
Okay.
you off. Only two types. And I believe that was week 4, which means in terms of my slides, that would have been session 2.
Okay, perfect. Thank you.
Yeah. It's not complicated though, so I'm sure you can just look at it yourself.
Yeah.
All right, here we are. So I didn't put the solutions on the slide, so you're gonna have to make note of anything that you really need. In terms of answers. Something in the chat? What's up? Oh, there you put that. Okay, cool. So guys, do you wanna share your answers, please? Actually, can you put it in the chat? Like, can you put it what you said, true or false? Okay, love to see it. Yes, guys, it is false. So if the test statistic gets larger, we are more likely to reject H0. Good. All right, question 2, let's see. Standard error is included in the inferential stats formulae because Okay, guys, B is the correct answer. So I want to ask Julia, why did you say C?
Because I wasn't sure if it's also included like the sampling procedure. I was unsure about it, but then I was like, okay, let's go safe and say it's both true.
Okay. So I'll tell you why A is not correct, is that when a researcher's sampling procedure is flawed, so that is different from the inevitability of a sample being not perfectly representative. Basically, a flawed procedure results in sampling bias, whereas the standard error is more about the sampling error that is inevitable. So, yeah, that's what that was about. Let's look at the next one. Okay, you're reading about a study done on children who show signs of neurodivergence. You're fascinated by how young boys are when they're diagnosed with ADD and ADHD, and you read that girls are diagnosed when they're significantly older. Unit of analysis. Yes. Have we got everybody's? Oh, okay. No worries, Julia. But yeah, D is the correct answer. So they are looking at children who show signs of neurodivergence. Yes. Okay, then a few questions related to that. So which test of significance did the study likely present results for? Julie, whichever questions you missed while on the call, just try and have a look at them now and see. Are we not answering because we're feeling insecure about this one? Yeah. Mm-hmm. No idea. Cool. Okay, so does one of the people who selected C want to explain their choice?
Well, I selected it because one of the variables is nominal because it's their gender, and the other one is age, which is ratio. So we have one nominal and one ratio variables, and we have to do a test of significance. So I selected two sample t-tests because of that.
Absolutely correct. I love the explanation as well. That's exactly the procedure you should be going through when looking at this information. So at the very least, you should have been able to recognize that what they've done is they've compared boys and girls. Okay, so a comparison between two categories. Instantly, that's the two sample t-test. Okay, but you can also do it by procedure. So there's two variables. One of them is nominal because it's gender, and there's two categories. And the other one is age because it's the age at which they were diagnosed, okay, which is ratio. So only option is the two sample t-test. Is that clear now looking at it for everybody who had no idea? Great. Okay, keeping with the same little story, let's have a look at 3.3. What are the main variables then? We already talked about it in the explanation, the previous one. So you should be able to know now. Right. It is D. Because if you chose a two-sample t-test, they have to be two variables. And so D is actually the only option that has both variables. But yes, biological sex and age. Lovely. Okay, let's look at question 4. A researcher rejects their H0 and accepts their H1. However, an error was made and H0 is actually true. What is this error called? Oh, we've got a variety. Okay. Okay, so your correct answer is B. So good job, Laura. So yeah, when you reject an H0 when it actually was true, okay, that's the type 1 error, and that's the error we really are trying to avoid making. Because rejecting an H0 basically means you're saying, oh no, previous research is wrong, which is a big statement to make in science. Okay, so rejecting a true H0 is a no-no. The type 2 error is when you retain the H0, but you should have rejected it. Okay. Cool. When two groups are assessed and compared on their population variance, what is this test called? You should know this very well. Lovely, it is indeed the Levene's test. Okay. Which of these statements about the normal distribution is false? Yes, it is D. Lovely. The normal distribution is unimodal, not bimodal. Out of curiosity, guys, were you answering these questions without looking at your notes or with looking at your notes? You can be honest. I genuinely want to know where you're at. Ah, that's great. Because you are doing very well. You're getting most of them right. That's good to know. All right. What is a negatively skewed distribution? Okay, I'm a bit concerned all of you said A, because that means there's a flaw in maybe the way that I presented this to you. But a negatively skewed distribution, actually the mean has shifted to the left, because the left side of the distribution is the negative side. So it should be B, actually. All right. This should be fresh in your mind. Which of the following is a measure of improvement in prediction of the regression line when compared to the mean? Okay, we've got 3 A's, and that is correct. Your SSM, your model sum of squares, does represent the improvement in prediction. Which of these represents the difference between what we predicted for Y and what actually occurred in the sample? Very nice. Prediction error, that is correct. It is B. Okay, and last one. In a regression line formula, what is the value of Y when x equals 0? Good. It is indeed C. It is the value of the B0. So you guys, you're doing very well. Okay, you're going to do amazingly well on your theory, on your multiple choice. So good job. Cool. Let's move into the open questions. Okay. Have a ton of fun. I would like you to try do this on your own. And if you feel really stuck, then speak up. Then I'm happy to look at stuff with you. Okay, but there's another regression question that I would like you to do completely independently. So try and then let me know. When you're finished with this one, just let me know in the chat, okay? Just say done. There, I have one done in the chat. Does anybody need more time? Okay, you do. All right. Okay, I'll give you a few more minutes. Okay, looks like we're done. Let's have a look. Okay, so what proportion? Oh, the solution's all at the end. Give me one sec. I moved all the solutions. One sec. I do want to show you the solution for this one before we do question 2. Right, my PowerPoint is being awful to me. Okay. Here we go. Okay, here are your solutions. So, in this population, 7.9% of the variance in life satisfaction can be explained by trust in others. Your predicted life satisfaction score is 5.738, the value of the B0. What's this one? So if X is 8, so 8 hospital beds per 1,000 people, then your predicted life expectancy is 7. Oh no, sorry, I'm thinking of the wrong variables. Okay, my bad. If you score an 8 on trust in others, then your life satisfaction score is predicted at 7.82. Okay, your F-test hypotheses should be in this population, R-square is 0, life satisfaction cannot be predicted by trust in others, and the non-directional version of the H1. And your conclusion of the F-test, so we can reject the H0 and accept the H1, that in this population, R-square is not 0. Life satisfaction can be predicted by trust in others. The R-square is 0.079, P is less than 0.001, and F is 1713.06. T-test. So in this population, the effect of trust in others on life satisfaction is 0. You can also write trust in others has no effect on life satisfaction. That's also fine. Your conclusion of your t-test should be we can reject the H0 and accept the H1, that in this population, the effect of trust in others on life satisfaction is not 0. Trust in others has a positive, weak, and significant effect on life satisfaction. Your P is less than 0.001, your T value is 41.39, and your beta is 0.28. Did we get this right, guys? Give me a thumbs up.
Yeah, I got everything right, but can you go, or at least, the first question, I wrote down another statistic. Can you go back to the question so I can check what I wrote down?
Oh, sorry. My PowerPoint is being a bit annoying. I think I might have to switch to PDF. Give me a sec. Yeah, give me one sec. I'm going to switch to PDF. Maybe this works a bit better.
Oh yeah, I see what I did. I wrote down R and not R square.
Okay.
Oops, okay.
Can I
All
have
good.
a question?
Sure, yeah.
So, do we need to round the numbers here, except the test significance? Or test statistics, sorry.
Yeah, so usually you round the numbers to 2 decimal places. Your p-value is never rounded. You always need to provide all 3 decimal places of the p-value. And I believe for the regression formula, when you include your B0 and your B1, you actually do need to use all of the decimal places, like as it appears in the output. But like for your beta, you can round to 2 decimal places. and your test statistics as well.
Okay, thank you. But they told us to not round the test statistics.
Really?
Mm.
Because they do it themselves in the lectures, which is weird. Okay. Listen, if they said don't round the test statistics, then I'm not going to tell you to round it. So you can put the full test statistic there.
Okay.
They always round the test statistics, yeah. They can't decide what they want from you. Okay. Next question. Can you guys read this okay? Yeah, okay. I might be able to make it a little bigger. Yeah. Cool. Okay, I've got one done. Does anybody need more time? Okay, let's take a look at the solution. Girl, there we go. Okay. Okay, so for one, your complete formula looks like this. Okay, if your two x values are 6 and 5, you would have gotten a predicted y value of 5.31. Okay, 3. The R square is the proportion of the variance in the DV that can be explained by the IVs. In this regression model, 10% of the variance in satisfaction with democracy can be explained by cultural life enrichment and immigrants make country a better or worse place. Okay, number 4, yes, the model is significant because the p-value of the ANOVA is less than 0.001. This is a multivariate analysis. Okay, and your specific effects would be in this population, immigrant cultural life enrichment has a positive, weak, and significant effect on satisfaction with national democracy, P and beta. In this population, immigrants make country a better or worse place has a positive, weak, and significant effect on satisfaction with national democracy. Yes, Laura?
I have a question about 6. Is when we go to the output, beta was both of them were positive weak, right? Does it
Yes.
always have to be like, do they all have to be the same, like always positive and weak, both of them, or can one be positive and weak and one positive and strong, or does it have to be the same always?
No, they can absolutely be different. You can have one that's very weak and the other one that's very strong and positive and negative. You can mention no, they've got nothing to do with each other in that sense. You've got to just base it on their beta. I think the examples we've done just happen to have very similar betas.
Okay, thank you.
And we don't have to say like if the satisfaction goes up by 1, cultural life goes up by 0.144.
No, so what you just described is if they ask for, please describe the value of the B1 in plain English. That's what you just did. So it wasn't a question in this example. One sec. Sorry. So you were looking at the unstandardized coefficients B column, right? So for B1, yeah. If they ask you, okay, please explain what that B1 means, then you would say when satisfaction with democracy increases by 1, then, sorry, that's the dependent. I'm tired. Sorry, when cultural life enrichment increases by 1, then satisfaction with democracy would increase by 0.144. Does that make sense?
Yes, thank you.
So guys, I'd like to take another break. It's not quite where the break is not quite planned, like in the content where I want it to be. But yeah, I would just like to take a break now. If you guys could come back at 12:17, that would be great. And then we'll work on the rest. Okay, guys, we're back. I was just sorting out my PowerPoint. Alrighty. Next question. Are we all back, by the way? Give me a thumbs up, just so I can see. Okay, guys, I see a few of you are done. I'm going to move on to the next question. And then I think after we do question 4, I want to go through the solutions for question 3 and question 4. Okay, I have one done. Anybody else done? Need more time? A bit more time. Okay. I'll give you like a minute or two and then we'll go through. All right, guys, I'm gonna go through it. I'm gonna skip ahead to where all the solutions live. Okay. So this was your question 3 solution. It was for your confidence interval. Okay. Did everyone get the correct answer? I didn't put the conclusion here, like the full conclusion. But with a confidence interval, you just say that we can conclude with 98% confidence that the population mean for this variable lies between 5.07 and 50.93. Okay. No issues? We good? We can move? Cool. Let's have a look at question 4. Okay. I left out the hypotheses and stuff just because, you know, it's an easy H0. You literally just copy paste all those percentages from the question. And the H1 is non-directional. So you would just say that it is not true that and copy paste the percentages. Okay. How did you guys do? Good. I'm glad to see you getting them right. And asking again, are we doing this without our notes? Very nice. Lovely. Okay. I'm going to travel backwards now to question 5.
I'm so sorry. Here, age null was it is true. I always mix it with age.
Sorry,
Like
I
it's
missed
always
that.
with the goodness of fit. That like for age 0, I put like it is not true.
No. For your H0 is that it's like copy paste all the percentages from the question. So what were these percentages? I don't even remember. So basically your H1 is when you say that it is not true. Because your H0 is the expectation based on previous research. Hold on, let me just exit this for a second. Okay. Yeah. So your H0 would be that 40% prefer party A, 35% prefer party B, and yada yada. Your H1 is that it's not true, that 40% prefer party A, and yada yada yada. Okay. So don't get into the habit or fall into the trap of thinking that H0 is always there is no, or it is not the case, or like it's a negative. It really does depend on the test. The whole point is, what is your baseline of knowledge? Like, what do you know based on previous research? And for the chi-squares, that would be the expectation, which is what these percentages are. They're an expectation based on previous knowledge, and then the observed is what actually happened. Okay, let's do question 5. Okay, I see some people are stuck.
Yeah, I'm a little bit stuck.
Okay.
So, I thought it's about the Z transformation, like with this formula,
Mhm.
and then looking up the calculated values in the Z table. But I was like plugging in the population SD and the mean and also the two values into the formula, and I got two Z values. But when I looked it up in the table, it didn't make sense, the numbers I got from the table. So maybe I did it wrong.
Okay. Um, well, tell me, let's see if we can find where exactly it went wrong. You find the correct solution. Okay. So what were your two Z values that you got after doing the formula?
So the first Z value I got was -3,
Uh-huh.
and the second one was 0.25.
Yeah, those are perfect. So, remember what I told you about when when test statistic values like Z values, T values, chi-square values, when they're negative, we can completely ignore the negative because we only look at the absolute value, which means it's positive form. So basically, you would look for 3 in the Z table because
Mhm.
there are no negatives in the Z table, obviously. So you should find the correct
Yeah, I did look it up and it was 0.84.
0.84. For which one? For the Z value of 3.
Yeah. So maybe I did look up the values wrong in the table. Like maybe that was my mistake.
Maybe, yeah. Yeah, maybe you've selected the wrong column.
I selected column B.
Okay, so you selected the correct column. You have the right values. What did you do wrong, go?
I don't know, like I also for the second one, for the 0.25, I got 0.67.
No. Okay. I'm gonna put the Z table up on screen because I think we need to deal with this.
Yeah, because my next thing I wanted to do was adding them up, but I'm far above like I wanted to make percentages out of them and then add them up, but I'm
Mhm.
far above 100, so I think it doesn't make sense.
Yeah.
Did you maybe like confuse this because I'm looking at the C table? Did you confuse this with the other test where you have to look like we have to look up 25% or something? I see that the C value for 0.67, which you had, is 2486. So were you like looking for the 0.25 in the table?
Yes, I was.
Yeah, so you have to look up the C value first in the table. So you have to look up 0.25 in the A column.
Oh, and then get my
Yeah,
values from the B column.
yeah. So you look up 3 and 0.25 in the A. If I'm right, I don't know, but like that's what I did. Um, you look it up in the A column and then your value is in the B column.
Oh, okay, yeah, then I switched it. Then I did it wrong. Thank
Yeah.
you.
So you're just mixing up what you do when you have an alpha and you're trying to find a Z critical. Because then you choose the C column and then you work your way back to the A column, right? Whereas this kind of question, you start in the A column and you choose between B and C.
Yeah, okay, that makes much more sense. Thank you.
Cool. Okay, I'll give you a moment just to complete the question and then we'll look at the solution. Are you ready for solution? I'm gonna do it anyway. So when you get access to these slides, I haven't uploaded them yet, but I'll do so when the session's done. There are more questions and the solutions, so you can continue working on it this afternoon. Here it is. Okay, this should be your solution for that question. How did we do?
Can you remind me only when do you what's the difference between when you subtract the two percentages and when you add them up? Because
Okay,
I
so
like by chance did it right, but I wasn't really sure if I should subtract or add.
okay. So it is logical, like in terms of when you look at what you, this is why drawing it is important. So if they are asking about the area between 5 and 18, the only reason you split the areas up is because of the way the z table works. You can only ever choose the area between mean and z, right? So you just have to do it in two parts. But you see that it's logical that you would, like they want the total area and it's right next to each other, so you just add them together.
When did we subtract them? We did
Okay,
subtract them at some point, right?
we did. I was just explaining why this is an add.
Oh yeah, okay.
So does that make sense at least?
Yeah, that makes sense.
Okay. When you subtract, it's when the area they ask about doesn't touch the mean at all,
Oh right.
go out into the tails. Yeah.
Yeah. Okay.
Everyone else is good, I'm assuming, on this one. Go back. Which one do I want you to do? Not this one. Okay. There isn't really time to start a new question. So I think maybe I'm going to let you guys work on this, the rest of this yourself, once you get the slides. And if there's any questions on any of the content, any of the weeks that you're not sure about before we go, I don't know why that's not there. If there are no questions, I'm going to ask you one more time. So this is really important also for our feedback, because this is the first time that Grade Guru has run these trainings for stats for IPCOM. I've obviously taught this course before a lot, but how did you find it? How prepared do you feel for the exam now, where you're at? Any verbal feedback as well would be appreciated. It's always nice to hear.
I thought it was super helpful. Thank you very much.
Okay,
Like,
good.
I think in the end, when I now look at all the stuff we have to do, it's not the hardest thing ever. It's just a lot to remember and a lot of rows to learn so that you know what formula to pick and everything. I think that's the hardest, but I don't know how I would have done it without you, honestly. Like, I don't know how to go about it otherwise. But yeah, I would say like an 8, I think is pretty realistic, which is crazy for me. I don't know about the other girls in here, but yeah.
Okay, that's great. Thank you for that.
Yeah, it was the same for me. So without you, I would have been totally lost. Also because like you have so many different sources where you get the knowledge from, like lectures, tutorials, and then readings. And this was really nice to like get an overview and to really know, okay, what is important, what do I have to know, and what is not that important. So it was really helpful. Also for SPSS, it was all really good. Thank you.
Okay, good.
Honestly, like both of them said everything I wanted. So like also for me, I don't know how I would have gone through it and understood it, but now I would say an 8 too. No.
That's great. Really happy to hear that, guys.
I also agree with what the girls before have said. I think it was very helpful. Thank you.
Okay, great. I'm gonna ask you a favor, and it's completely up to you. But I'm gonna put my email address in. Actually, I'm gonna put my WhatsApp number in the chat. And I'd actually really love to hear like how the exam goes when you get your results, just like for funsies. And especially if if you start off learning, like doing the revision for this course and you feel really lost and you come out of the exam with an 8, like that's nice to hear for a tutor. So there, it's in the chat. Awesome, guys. Good luck for your exam tomorrow. And I'm sure that you're also submitting a portfolio or something. So good luck for all that. And thanks for joining.
Thank you
Thank
very
you.
much.
Bye. Thank you.
Goodbye.
Bye bye.